matrices, a little bit more. We're gonna finish up matrices this week. Plan to take a test by Friday is the plan. In order to finish that up, there's really like one main idea we got to talk about, and that's how to solve a matrix equation. In order to solve a matrix equation, we need to be able to find the inverse of a matrix. Think about like 5 times x. How do we get rid of the 5? We divide by 5. We do the inverse. Well, what about matrices? Is there any way we can actually divide matrices? And the answer is no, not really. So what we need to do is multiply by the inverse. So we can multiply matrices, but we need to be able to multiply by the inverse. In order to find the inverse, though, which is what we're going to talk about at the end of class today, we need to be able to find the determinant of an inverse. And every square matrix has a determinant. It is a real number that describes that matrix. And it's only for square matrices in which the rows and the columns are equal. To denote the determinant of a matrix, we can use this notation, something like that, the determinant of matrix A, or we can use what look like absolute value bars. They're not, but that's what they look like. Absolute value bars of A, which is really the determinant of A. And every square matrix in which the rows and the columns are equal, the same number of rows and the same number of columns, has a determinant. Every single square matrix has what we call a determinant. You need to be able to find a 2 by 2 determinant by hand. Anything bigger than 2 by 2, you would not do the same way as we do a 2 by 2. And we're going to use matrix calculator for those. So in order to find the determinant here, it's going to be the main diagonal, A times D, the main diagonal minus the backwards diagonal. So the main diagonal multiplied together minus the backwards diagonal multiplied together. And that's only for 2 by 2 matrix. If I were to put a 3 by 3 matrix up here, you would not do it the same way. Similar, but not the same way. Because now we have more diagonals to look at and stuff. So how do we determine this thing called the determinant? Well, really, it's not super complicated. If we let that matrix in number 1 be A, we want to find what we would call the determinant of A, or we can call this this way, using what looks like the absolute value bars. That means the same thing. Or even if we didn't give this matrix a name and we just used the straight lines and put 9, 4, 3, 5 inside the straight lines instead of the bracket, that would also mean the determinant, not the matrix, but the determinant. And if I intended for that to be the determinant, I would not use brackets. I would just use the straight lines. Now, how are we going to find that? We're going to multiply the main diagonal together, which in this case would be 9 times 5. And we're going to subtract the backwards diagonal, which would be 4 times 3. Multiply the main diagonal, multiply the backwards diagonal, and subtract those two numbers. 9 times 5 is 45. 4 times 3 is 12. And 45 minus 12 is 33. 45 minus 12 is 33. Number 2, let's call the matrix in number 2. Let's call it B. And why do we need to know how to find the determinant? We need to be able to find the determinant so that we can find the inverse. Why do we need to be able to find the inverse? So that tomorrow we can solve matrix equations. We can't divide by matrices. We're going to have to multiply by the inverse. So if this is matrix B, we want to find the determinant of matrix B, which is going to be the main diagonal, negative 2 times 8, minus the backwards diagonal, 7 times negative 5. Be really careful with your signs, especially when you're subtracting negative numbers, because that actually ends up being plus 35. So -7 times -5 is actually positive 35. So it's really easy to leave a negative off. We get -16 plus 35, and that is equal to 19. That is equal to 19. I'll give you maybe like a minute or two to do number 3 and 4, and then I'll give you the answers and work them out if I need to. Try number 3, try number 4. If we can't find the determinant, we're not going to be able to find the inverse today either. And the method we're doing only works for 2 by 2 matrices. The only thing we need to be able to do without matrix technology like this one. Number 3, you should have got 64 for number 3. For number 3. If you're done with number 4, the answer's on the board. You want to check the work. Be careful with the minus signs. How do we get number 3? How do we get number 3? 8 times 7 is 56. 8 times 7, so let's call this C. The determinant of matrix C would be 8 times 7 minus -2 times 4. That's where we got to be careful. My guess is you probably didn't include the minus -2. You probably just said -2 times 4. But it's definitely minus -2 times 4, which ends up being 56 plus 8. Yeah, 56 plus 8 is 64. 56 plus 8 is 64. Number 4, you should have got 29. Any questions about number 4? Should have got 29. 21 plus 8 should have ended up being 21. 7 times 3 is 21. -2 times 4 is -8. But it's going to be 21 minus -8. So it actually ends up being 21 plus 8. All righty. Rolling right along. The n by n, we call this the identity matrix. The n by n identity matrix is a matrix that has ones on the main diagonal and zeros everywhere else. So the main diagonal is going to be this one from the top left down to the bottom right. So the main diagonal is going to have ones on it. It's got to be a square matrix. And it's going to have zeros literally everywhere else. Why do we need to talk about this identity matrix? It brings this idea in when we start talking about inverses. It's going to come up again when we start talking about inverses. So this is why we talk about the identity matrix now. This idea of identity property is nothing new. You've been familiar with the identity properties in math your whole life, pretty much. Think back to when you're like 3, 4, 5, you were just first learning how to add. And maybe somebody was like trying to trick you, give you some trick math problems, you know? And they would say like, oh, well, what's, they would tell you a number, and they would say a number plus blank is equal to the same number that we started with. What number would go in that blank? Any number plus blank is equal to the same number? That number is 0. Well, guess what? That is the additive identity property. Anything plus 0 equals itself. You've been familiar with that for a really long time. And then maybe a little bit later on in life, you started learning how to multiply, and everybody was trying to give you all these multiplication problems, and they're like, oh, what's 1,000 times 1? And what's 28 times 1? And what's 22 times 1? And you're like, and then you finally realize that, hey, anything times 1 is itself. And that is just the multiplicative identity. Anything times 1 is equal to itself. Well, matrices have this identity also. It's kind of like adding and multiplying together, because when we multiply, we have to add also. But there's this matrix identity that if we take a matrix and multiply it by the identity, so we take some matrix, call it A, and we multiply it by the identity, it doesn't change that matrix. It's still the same matrix. 5 plus 0 is still 5. 12 times 1 is still 12. A times I is still just A. And it doesn't matter what order we multiply it in. I know before spring break, we talked about, hey, the order for multiplication matters when we talk about matrices, but not when we're talking about the identity, it doesn't. So A times I and I times A just give us that matrix that we started with. And just to kind of show you an example of that, we have two matrices here together. We're going to multiply them together fairly quickly and move on. But just to show you that, hey, a matrix times the identity, call this A, times I is equal to, hopefully, A, because that's what we just said. So let's figure this out. How would we multiply these together? First row times first column. We're going to multiply the 5 and the 1 together, the -2 and the 0 together. So we get 5 times 1 plus -2 times 0. That's first row, first column. I'm just writing everything out. You don't have to. We've already learned how to multiply by hand. But just to refresh, we're going to be doing lots of multiplication by hand tomorrow. But just to refresh what multiplying looks like. So that's first row, first column. That's where it goes. And then we're going to look at the second column. We get the 5 times 0. And the -2 times 1. So plus -2 times 1. And that's the second column. First row, second column. So that's why it goes in the first row, second column of our answer matrix. And then we're done with the first row. Like, hey, I've multiplied the first row by every single column. So now we're going to multiply the second row by the first column. We get -7 times 4 and 4 times 0. -7 times 4 plus, I'm sorry, -7 times 1. -7 times 1 plus 4 times 0. And then we're going to do the second column as well. The 0 and the 1. -7 times 0 plus 4 times 1. And if we add all those things together, what do we end up with? We end up with 5 times 1 is just 5 plus 0 is 5. 0 plus -2 is -2. -7 plus 0 is -7. And -7 plus 4, I'm sorry, 0 plus 4 is 4. And what do we end up with? We end up with that matrix that we started with. So anything times the identity matrix is just itself. Well, why do you talk about that? We talk about that because we kind of have to know that in order to talk about matrices and their inverses. Because if you were to take a number like 2/3, and multiply it by its multiplicative inverse, which is 3/2, what would you get? You'd get 1. What is that really? That's really like A times A inverse equals the identity, right? That's the same idea, just with a number. And we can do adding and subtracting as well. What if we had a number like 5 and we added a number like -5? That's a number and its additive inverse. What is that going to equal? The identity, the additive identity. So a number plus its additive inverse is equal to the identity. That's the same idea that we're about to talk about when we start talking about these ideas of inverses. So two matrices A and B are inverses. Two matrices A and B are inverses of each other. If what? If their product is the identity matrix. And it doesn't matter if you do A times B or B times A, we have to multiply them together. We have to get the identity matrix. And that's why we talked about the identity matrix for 3 minutes, because of that right there. So an n by n matrix, a square matrix, has an inverse if and only if the determinant does not equal 0. And I'll show you why, if the determinant does equal 0, that matrix doesn't have an inverse. But there's this property that shows up that says, hey, if this matrix is going to have an inverse, its determinant cannot be 0. If its determinant is 0, the inverse does not exist. And what is the symbol for the inverse of A? The symbol for the inverse of A is A with the little -1, the same little -1 that you should probably remember back when we learned about inverses. We did an entire unit on inverses. I said second semester. It was the beginning of this semester. We had f of x, and then we had f inverse of x. It's the exact same notation there with the -1. All right, so how do we find the inverse of a 2 by 2 matrix without a matrix calculator, without technology, without a program that just does it for us? It looks really complicated. It does. It looks really complicated. If you look at that, you're like, huh, what's that mean? Well, this right here means the determinant. That's that same number that we found earlier. The main diagonal multiplied together, A times D, if we're using those letters, minus the B and the C. That's the exact same numbers that we found earlier. That's just the determinant of that matrix. And now what are they doing with the letters inside the matrix? They're kind of rearranging them, switching them, changing them. And why are they changing and switching them the way they want? Because they know, and the reason they're doing that, because they know that A times A inverse has to equal the identity. And there's really only one way that can happen, and that's rearranging it the way that it's being rearranged here. So what's happening to the A and the D? The A and the D have changed positions. So the main diagonal switches positions. The A and the D. The A and the D switch position. What about the backwards diagonal? What about the B and the C? The backwards diagonal, they actually don't change position. The B and the C are actually in the exact same spot, but now they're the opposite sign. So the backwards diagonal switches signs. So the forward diagonal switches positions. The backwards diagonal changes signs, however you want to say that. And that is going to give me a matrix in which, if I multiply it by the original matrix, all of this stuff is going to happen, where that the answer is going to be that identity matrix 1, 0, 0, 1. Lots of things are going to cancel out. Lots of things are going to multiply to give us 1. So our first example here, we want to find the inverse of matrix A. The first thing we need to find is really this determinant of matrix A, and that's going to go right here in the denominator. Really, that's just really the denominator. So what do we have? We have 3 times 5 minus 8 times 2. That's all that is. That's just the determinant of that matrix. And what are we going to do with the elements of matrix A? We're going to change them around a little bit, maybe switch some signs. So the main diagonal, the 3 and the 5, what's going to happen to the 3 and the 5? They're going to change position. The 3 and the 5 are going to change position. What's going to happen to the backwards diagonal, the 8 and the 2? The 8 and the 2 are going to change signs. So it becomes -8 and -2. And that is equal to the inverse. We probably don't want to leave it like that. We probably want to make it look a little bit nicer. But this is the inverse. We get 1 over 3 times 5 is 15. 8 times 2 is 16. 15 minus 16 is -1. So we get 1 over -1 times 5, 8, or -8, -2, and 3. So this is just a scalar multiplication at this point. We learned that before. And how do we simplify scalar multiplication? We just distribute that scalar to every single element in that matrix. So we're just going to multiply this by all of those. So we get -1 times 5 is -5. -1 times -8 is +8. -1 times -2 is +2. And -1 times 3 is -3. And that -5, 8 to -3 is the inverse, the matrix that we first started with. And you're like, why does that matter? It matters because if we can find the inverse, we can now multiply both sides of a matrix equation to get rid of the A on the left side. Because the A and the A inverse now are going to multiply to give us the identity matrix. And just to show you very quickly, let's just multiply A and what we just found to be A inverse together very quickly. A inverse would be -5, 8, 2, and -3. Now what do we get if we multiply these together? We get 3 times -5 is -15. 8 times 2 is 16. So we get -15 plus 16. 3 times 8 is 24. 8 times -3 is -24. 2 times -5 is -10. 5 times 2 is +10. 2 times 8 is 16. And 5 times -3 is -15. If we add all that together, -15 and 16 is 1. 24 and -24 is 0. -10 and 10 is 0. And 16 and -15 is 1. So we get 1, 0, 0, 1. And we're going to talk about it a little bit tomorrow. Now that matrix that was on the left, it's not there anymore. Because what we might start with and what we're going to start with tomorrow is going to look something like this. Tomorrow we have 3, 8, 2, 5, 3, 8, 2, 5 times some matrix X. We don't know what that matrix is, but that's going to equal this other matrix. And I'm just going to put question marks here because I don't know what that is at the moment. But if I want to get X by itself, what do I have to do? We have to multiply this matrix times its inverse, because then I'm going to get this matrix times X. And what is the identity times anything? Just X. So then the left side is just X at that point. And then we can do the same thing on the right side, and X would be by itself. We will look at that tomorrow. We will solve those types of equations tomorrow. Number 1, let's call number 1 matrix A, and we want to find A inverse. We want to find A inverse. 1 over the determinant. What is the determinant of matrix A? This is something that I would probably figure out off to the side. 3 times 2 is 6. 2 minus 4 is 8. 6 minus 8 is -2. So I'd probably just maybe figure that off to the side. Like, hey, determinant A is going to be 6 minus 8. 3 times 2 is 6. 2 times 4 is 8. 6 minus 8, -2. All right, cool. So that's the 1 over the determinant. And then what's going to happen to our matrix? The main diagonal, the 3 and the 2, are going to change positions. The 3 and the 2 are going to change positions. The backwards diagonal, the 2 and the 4, not going to change positions, but they are going to switch signs. So -2 and -4. Now tomorrow, it might be easier to leave the -1/2 out front to start with. And do the -1/2 at the very, very end tomorrow. We'll get there tomorrow though. But for today, I just want you to go ahead and multiply each element times this number on the outside. So we get 2 times negative 1/2 is negative 1. Negative 1/2 times negative 2 is positive 1. Negative 1/2 times negative 4 is positive 2. And negative 1/2 times 3 is just negative 3/2. It would probably be better just for you to write fractions today. Well, can I put the decimal? Well, it depends. 1/3. Let's talk about 1/3. Talk about 1/3. Can I just put the decimal? What if the fraction was 1/3? What decimal would you write down? Probably. You would probably write down what? 0.3. Or maybe you would even write down 0.33. Is 0.33 and 1/3 the same thing? Not exactly, right? Not exactly. So if we want the exact answer is going to be 1/3. What's 0.33? 0.33 is going to be rounded. And we don't really like rounded answers in math, unless we're talking about real life application stuff. So it'd probably be best just to write the fraction down today. All right, we're done with number 1. Let's try number 2. Let's call number 2 matrix B, maybe, given a name. And then we're trying to find B inverse. 1/. What is the determinant of matrix B? Let's find that off to the side. The determinant of matrix B. 7 times 6, 42, minus 14 times 3, which is also 42. And 42 minus 42 is 0. So for our inverse, we get 1/0, 1/0, 1/0, 1/0, 1/0. Anybody see anything wrong with that so far? We're good? I can keep going, I can stop. The 7 and the 6, if we could find the inverse, the 7 and the 6 are going to switch. The 14 and the 13 are going to change signs. Anybody see anything wrong with that yet? Yeah, there's a big thing going on there. What can we never, ever maybe do in math, Tommy?
Never put a 0 in the denominator.
Yeah, we can never put a 0 in the denominator. We can never, ever divide by 0. Why can you not divide by 0? It's not possible. We'll talk about it more in our next unit. We're going to do a lot about this dividing by 0 part. But this is not possible. And since this is not possible, the inverse does not exist. Remember, we wrote down earlier in our notes, hey, if the discriminant is equal to 0, what did we write? We said, hey, if the discriminant, or not the discriminant, the determinant, if the determinant is not equal to 0, oh, hey, if the determinant, it has an inverse, if and only if the determinant not equal to 0. So if the determinant is equal to 0, does it have an inverse? No. And what does it mean for it not to have an inverse? In this case, take this matrix 7, 14, 3, 6. If I multiply that by any other matrix, I don't know what this matrix is. This would be our inverse matrix. There's no way that this will ever equal the identity matrix. That is not possible. Okay. And since that's not possible, we do get a determinant of 0, and then the inverse doesn't exist. But you cannot take a matrix, in this case B, that doesn't have an inverse, that the discriminant is equal to 0, and multiply it by some other matrix that we can maybe call the inverse, and get the identity matrix. You will never get this 1, 0, 0, 1. It'll never be equal to that, ever. I don't care how many times you try. I don't care how long you try to come up with that number. It'll never work. So that's why this matrix inverse in number 2 does not exist, because there's no number that I can multiply, no matrix that I can multiply this by to get our identity matrix there.